Okay, so our second speaker is Alex Kavvos from University of Bristol, and he will talk about algebraic effects.
Thank you very much. First of all, apologies. This is a talk about denotational semantics, okay? So it's about three things. It's about adequacy, that's clearly a technical thing. It's about algebraic effects, which you might have heard about. And it's revisited, which means someone else has done it before me, but I've done it again, and I'll explain how. So, oh no. Oh, no. Slideshow, there we go. Okay, so what is adequacy? When you do semantics of programming languages, you usually do a little operational semantics. And often, when you do operational semantics, you've got some terms, and they step from one to the other. What's great about that? It's easy, it's nice, it's perfectly understandable. What's bad about this, it's almost impossible to reason about, as anyone who's done any program verification has ever thought about. Okay, but this induces a notion of operational equivalence. You know when two terms are the same, exactly when they either have the same reductions or in any context they do the same thing. Denotational semantics, on the other hand, is a translation to mathematics. You take your program, you map it to something in mathematics, and you have 2,500 years of tradition you can draw from. Okay? You only draw from the last maybe 50 years, but you still could. And adequacy is the property that if you discover something to be true using denotational semantics, then this will be true operationally as well. So for example, if you prove that the denotation of two terms is equal, then these terms should behave the same when you run them operationally. If you don't have adequacy, there's no reason to have denotational semantics. You need it to say anything at all about how programs run from the mathematical description. So this has been shown before for algebraic effects, but only finite true ones, by Plotkin and Power in a really influential paper, FOSSAX 2001. It was an invited talk. But the proof was difficult, and it only covered certain things that I wanted to do more of. So I wanted to do functional logic programming. There'll be a paper later this year, and that has an infinitary algebraic effect, which you couldn't do without proof. So I set out to do a simple logical relations proof, as simple as it could be, in order to cover this case. But I also did a lot more in the process. Okay, so really quick recap. What are algebraic effects? You might have heard a lot of things about them. The idea of function programming is that you've got a closed program, you put it in GHCI or your favorite functional language, out pops a value. Algebraic effects do much more than that. Algebraic effects are really just system calls. An algebraic effect is something that you issue, there's some kernel, hypervisor, whatever you want to call it, which takes this signal, does something, gives you back a value, and then you continue with this value. So I will use that notation, op, for an algebraic operation, which sends sigma and receives tau. These sigma and tau have to be serializable, they have to be first order things. It's really important that they are. If they're not, you get into trouble. For example, to have a global memory that holds one natural number, you can write this natural number and receive the unit value, or you can read this natural number by which you send the unit value and you get back a number. So here's a little program in this notation. Write to read x, return the successor of x. Algebraic effects produce these things called interaction trees. You can see an interaction tree on the right. The first node is the write instruction. Then you do, that only has one possible continuation. Then you read, and depending on what you read, you return the successor of that. If you read 0, you return 1. If you read 1, you return 2, and so on and so forth. There's nothing in algebraic effects that tells you your memory has to be correct. Okay? So your memory could return the wrong value. That's an equation that you put on algebraic effects later on. Okay, one of the main technical innovations in this paper is using something called call by push value. I don't have time to go into it here, but if you don't know about call by push value and you like effects, learn about call by push value. Just go away and learn about it today. It's an amazing innovation. It fixes almost every technical problem you might have. It fixes the order of things. It's wonderful. But the main thing is you've got values on one side, which are immutable mathematical things like numbers, sums, products, and also these magic things called funcs, which are really just a frozen computation. And on the other hand, you've got computation types, which are really types that describe an imperative thing. The most basic thing is f of a, which a computation of this type will return a value of type a. Interestingly, a function here is something slightly effectful. It's something that pops an a from the stack and continues as something else. There was a fantastic talk earlier today by Max New on reading these as types of stacks. And you've got two kinds of terms, and if you know any Haskell, you'll recognize return and bind, but in slightly different notations. The operations are given by op, which takes an argument v of type sigma, which should be the right thing, and the continuation receives back something of type tau. This is the basic setup. And notice that operations can only have first order types, serializable things, no functions. Okay, you can give a really simple operational semantics. You can either look at this slide or I can just tell you. You have two reductions. One is your usual pure reduction of terms. The other one is the effectful reduction, which says I'm sending to my kernel the value v, and my kernel responds with my value w. And what you do when you have an operation, you can send that, receive w, and then you continue as the body with w substituted for x. That's it pretty much. Here's a reduction where the memory malfunctions. You send it, you write 2, then you read it, and you get back something else, so you return 4 in the end. You can use this to define a map that for each computation gives you an interaction tree, the thing you saw before. Okay, denotational semantics, I could talk about this for hours. I'm not going to talk about it for hours. It's a very simple, standard domain theoretic semantics. The details are unimportant. All you need is you need a monad which supports your effects. So you have a return and a bind, and for each op, you've got something that allows you to interpret this into tx. So this op thing would take the value, and then for each possible thing that you could return a continuation and give you something of type t of x, and you need to satisfy this equation. This equation is the fundamental equation of algebraic effects. If you read it, it says if you do an operation with continuation k, and then you bind into f, you could do the operation now, take the result and feed it into k, and then bind that. So effects happen now, and they are independent of continuations. If you don't have this, your effects are not algebraic. What's not algebraic? Continuations. Okay, control effects, not algebraic. If you have all this, for example, a state monad supports write and read. And if you have this, you can define continuous functions for values and computations. Okay, observational equivalence, or operational equivalence. Standard thing you would do in a functional language. You'd say two terms are the same. If for any context you can put them in, they give exactly the same values. Jim Morris did this in 1969, and we've suffered ever since. But this doesn't work when you have algebraic effects. So the solution to this is to say, well, suppose you have a way of lifting arbitrary relations between two sets to monadic values of the same thing. If you have that, then what can you do? You could say, well, m and n are equivalent if you plug them into any context, which you can think of as a testing bench, you compute the interaction tree, and then you evaluate it in your monad that's related to the same thing for the other term, exactly when you've lifted the equality relation on values. So you generate related trees with the same values at the top, at the bottom. And this is not due to me, it's due to Francesco Gavazzo, who's done a lovely series of works on this. Okay, I'm just flashing this for your information. There's some axioms that this lifting needs to satisfy. This map from relations to relations. It's these axioms. They're not so interesting. For example, for the state monad, you say two memories are related. If for any input, they output, well, for anything that could be stored in memory, they output the same thing, and then the values they return are related. And these need to be compatible with everything in sight. It's unimportant what this is. You can easily derive it. Proof, biological relation. This is a very simple proof. This is the entire logical relation. There's nothing hiding here, nothing hidden under the sun. You define the logical relation at return types by lifting the relation of values, and you just need to decorate things just sufficiently. The usual lemmas go through, as you would expect in any standard logical relations proof. In particular, this is only a very little generalization of how Gordon Plotkin did it in 1977. And in particular, that proof is an instance of this for a very simple relator. Okay, this is also another slide not for you to read, but the idea, what I wanted to show you here, is that indeed the proof follows very simply. Nothing is hidden under the sun here. Well, everything is hidden in the particular axioms, but should the axioms hold for your relator, you can push everything through, pull these relations out. These relations, you know, compose to the value relation, and then you get that terms are related. Rinse and repeat for the other direction, and you are done. Whole proof. Only took me a year. Okay, I will be finishing a bit early, I suppose, but what I want to do from now on, an important thing to do here is to lift this to recursive types. So the language we have, if you go back to the language, does not have recursive types. It does have recursion on computations, but not recursive types. Recursive types are really important, as referring to Max New's talk again. Max presented computation types as a sort of discipline of typing for stacks. If you have such a discipline of typing, you could have functions of variable arity, right? Something that JavaScript has now is fully typed and perfectly compatible with theoreticians. So if you have recursive types, you can do all sorts of interesting things. But extending this to recursive types is always difficult. Logical relations on recursive types are difficult, at least if you don't want to make them guarded. But Andy Pitts' results from 1996, fantastic paper if you haven't read it, Relational Properties of Domains, should apply here with some contortions. The most important thing, though, is that a bunch of relational liftings used by many semantics researchers do not actually fit the relator framework. The axioms don't hold. So earlier today, for example, Pedro gave a talk where I think some of these axioms won't work. The question is, what's the difference here? There's a bunch of things like TT lifting due to Shinya Katsumata, or the code-density lifting more recently. They just don't satisfy these axioms. So you have to do something different. It's a bit of a question mark. If anyone knows the answer, I'd be happy to hear it. And finally, formalizing this might be a bit of a difficult thing, but it is certainly something on the cards. Someone would use suppose you'd have to use a domain theory library in Agda or Coq, which will be a little bit sad, but, you know, ways of writing more papers, I suppose. That's all I had. Thank you very much for your attention.
Okay, thank you for a great talk. Questions? Yeah, you can use my. Yeah.
Thank you. This is very interesting. So regarding the question of recursive types, do you envision some, I mean, since you have effects, you will need some step indexing, I guess, that goes beyond natural numbers. Do you envision that? Or?
I think it should be fine, but ideally I wouldn't like any step indexing at all.
I see.
So that's what the minimal invariant stuff does.
Okay. So
but
you
it's a bit difficult to do, and in particular it's not proof assistant friendly, which is why people have never done it. When people do these proofs and proof assistants, they use a guarded variant of domain theory, and they step index everything, and it all works out. But the cool thing is to do it without, and I don't know how.
Okay, interesting. Thank you.
Thank you.
Hi. Looks like a nice generalization. What I was wondering was, is it possible to relax the restriction that continuations have to be serializable values? Because sometimes you want to have operations that bind effectful things, right?
Yes.
If you want to encode things like control effects, you can do it with algebraic effects, but that requires you to do that. Is that a very hard generalization to do, or?
Okay, if I'm going to give you the mathematician's answer, which I often do, if your things are not countable, you don't have algebra. You don't have algebraic effects. You have something more than that. So you need at least some ordinal that bounds how big your values get. So the point is that these trees, these interaction trees, they're infinitely deep because they're co-inductive, and then infinitely wide because you have infinitely many results. If you don't put some bounds on the width, there's problems. Mm-hmm. It's an interesting problem. It's no longer algebraic effects. It's something else, I would say.
Okay.